Hi everyone, this is your instructor, Professor Churchian, and I'm looking at the Team 2 problem assignment, and I just wanted to make a quick video to help you out with this assignment and hopefully help you make a little more sense of it, especially one part in particular, which we'll get to in a sec. But the assignment deals with the Fibonacci sequence and its relation to the golden ratio. And the golden ratio is denoted by this Greek letter called phi. That's how you pronounce it, phi. So the goal is that you have to show in part 1 here, and again, it's based on the text, page 132, number 5, that when phi is raised to a positive integer power, that result can be written as some expression, some number a, plus some number b multiplied by phi, where these numbers a and b are Fibonacci numbers. So really what you're asked to do is to find these quantities, phi squared, phi cubed, phi to the fourth, and that will allow you to gather more evidence for this conjecture, right? That you could write every single one of them in terms of A, B, and phi. So that's what you're really doing. So if we take a look here, what we have is phi is our golden ratio, our special number phi, and I'm quickly going to remind you here that our Fibonacci numbers, our Fibonacci sequence is denoted, I'll do it here on the side, it's a 1, 1, 2, 3, 5, 8, 13, 21, etc. So to get the next number, you just add the previous two. Like 1 plus 1, that's 2. That's how you get that entry. 1 plus 2, that's 3. That's how you get the next number. 3 plus 2 added together, that's 5. That's how you get the next number. 3 plus 5 added together is 8, etc. So again, the goal is when phi is raised to a positive integer power, the result can be written as a plus b phi, where a and b are Fibonacci numbers. And here's what we mean by that. The hint in the book tells you that the value of phi is this, 1 plus square root of 5 all over 2. That's the actual value of this number. So if I try to square this number, which is what I've done here, it's the same as multiplying the number by itself. That's what it means to square a number, multiply it by itself twice. So I have 1 plus square root of phi over 2 multiplied by itself. But that's the same as multiplying the tops together and multiplying the bottoms together because they're multiplying two fractions. So it will give me 1 plus square root of 5, the quantity squared, divided by 2 squared, because I have 2's on the bottoms here. Or 1 plus square root of 5, the quantity squared, divided by 4. Now if you expand this top part, it means 1 plus square root of 5, that quantity squared, means multiply 1 plus square root of 5 times itself. And when you do that, you end up getting 1 plus 2 square root of 5 plus 5. Do this on your own and verify that this is true. You should check this out. On the bottom, I still have 4. Well, 1 and 5 added together give me 6. So really, I can write this as 6 plus 2 square root of 5 all over 4. Further, this is an even number. This 2 here that I'm multiplying by square root of 5 is an even number. And 4 is an even number. So I can divide every single term in this expression, in this fraction, by 2. And then I would get 3. 6 divided by 2 is 3. Square root of 5, because 2 times square root of 5 divided by 2 is square root of 5, and 4 divided by 2 is 2. All I'm doing is simplifying the expression by taking out a 2 or dividing through by 2, either way you want to say it. And here's the tricky part that I feel like I should help you with, and hopefully it can help you make more sense of this. When you have this number here, 3 plus square root of 5 over 2, it doesn't really tell you much. You don't see the relationship to the number phi you started out with. But look, you could write 3 as 2 plus 1. And I know it's not intuitive why, but here is why. If you write it this way, you have 2 plus 1 plus square root of 5 all over 2. I can represent this as 2 over 2 plus 1 plus square root of 5 over 2. I break this fraction up into a sum of two other fractions with a common denominator. I could do that. And look what happens. 1 plus square root of 5 over 2 appears, and that's the number phi. So I get 2 over 2, which is 1, plus phi. So you have just proved that what we started with, phi squared, is the same as 1 plus phi. Okay? And remember, our goal was to ultimately represent phi to any power here, to some power, as a plus b times phi, where a and b are Fibonacci numbers. And guess what? We just did it for phi squared because there is a 1 here, and there is a 1 here, so a is 1, b is 1, and both of these are Fibonacci numbers. And now look, for the next one, if you want to check what phi cubed is, here is a hint as well. Don't go through this multiplication. Instead, simply do phi squared, and let me make this a little nicer, phi squared times phi. Because phi squared times phi is phi cubed, right? When you multiply something to the second power times the same something to the first power, you add the powers to get the resulting power, which is 3. Why is this easier? Because I already know what phi squared is from the previous computation. It's just 1 plus phi. So I could replace phi squared with 1 plus phi and multiply that by phi instead. And what am I end up getting? Well, when I distribute here, multiply each of these terms inside the parentheses by phi, I get phi plus phi squared. But once again, I know what phi squared is because I just found it. It's 1 plus phi, so I could replace phi squared with 1 plus phi. And now I could combine the like terms. I have a phi here and a phi here. That gives me 1 plus 2 phi. So we have just shown that the thing we started with, phi cubed, is the same as 1 plus 2 phi. And once again, you wrote phi to some power as a plus b times phi, where a and b are Fibonacci numbers because 1 and 2 are consecutive Fibonacci numbers. So this pattern is what you're trying to show. For phi to the 4th, for example, you could just do phi cubed times phi and see what happens. And you should be able to get an answer eventually that could be represented as a plus b times phi, where a and b are Fibonacci numbers. I hope this helps.